Now we get to talk about joint variables and disjoint variables. Variables formerly known as mutually exclusive and non-mutually exclusive. Vocabulary terms and statistics seems to be in a little bit of a flux. Keep changing vocab. But the first thing we'll do is let's take a look at the probability map. Let's see, we have done fundamentals. We had video on discrete variable. We had video on dependent variables. That was a fun one, kind of a long video. And we talked a little bit about independent variables, but haven't gotten into the details yet. Now, we're right here. Right? So again, mutually exclusive, non-mutually exclusive, also known as disjoint and joint variables. So getting back to here, all right, probability map. Now, let's actually talk about joint versus disjoint variables. So let's get an example up on the board. Under disjoint variable, we're talking about hard drives. Computer store has 85 hard drives. 65% of those hard drives are brand A. 24% are brand B. Over here under the joint variable example, we have 40 students that were asked what they like to drink. 55 said they liked Sprite. 35 said they liked orange Fanta. And 10% said they liked both. The implication, of course, is that 55 said they only like Sprite. So what makes this joint, a joint variable, this a disjoint variable? Well, it all comes down to when you randomly select one. So over here, if you were to randomly select one hard drive, could it be both brand A and brand B? No. It can't be both. It's either one or the other. It can't be both. That's disjoint. If you randomly select one of these 40 students, could they like Sprite? Yes. Could they like orange Fanta? Yes. Could they like both? Yes. So both is a possibility with joint variables. So here both can't happen. Here both can happen. And that's really the difference. Now, when we start calculating probabilities, this is actually a very important difference. And we'll see how this plays out. Now, this hard drive question is just like the drawing a diamond from the deck of cards question that we talked about. That, if you were to draw or randomly select two hard drives, what's the probability that the first one will be brand A and the second one will be brand A? Well, it's just like that one. We'll go over this because it's good to review, but for the moment, I want to focus on this joint example. I can really try and work the details out of this one. Now, when dealing with a joint variable like this, what we're going to be using is a technique which you have done before, but maybe a long time ago and haven't used in a while. And this is a Venn diagram. So let's draw a Venn diagram of this question. Venn diagram. So we're going to have one circle that represents Sprite. We're going to have one circle that represents Fanta. Right? And of course we have an intersection of the two which represents those who like both. So we have Sprite, in which 55% said they like Sprite. Fanta, which we have 35%. All right, notice I'm kind of doing it on the outside, which denotes this whole circle is 35, and this whole circle is 55. And 10% said they like both. So this little space in the middle is 0.01, or actually 0.01. 0.1. Sorry. Now we have some questions we can start answering, such as, what's the probability of a randomly selected student liking Sprite? Well, that's actually a fairly straightforward question, right? 0.00 or 0.55, right? Or a 55% chance that a randomly selected student will like Sprite. Right, similar question, what's the probability of a randomly selected student liking Fanta? Right, equally simple, perhaps. 35% of all the students surveyed liked Fanta, so that's the probability. Well, here's another question, starting to get more interesting. What's the probability of a randomly selected student liking neither of them? All right, well, let's consider this one quickly. If you were to do it without thinking, you'd say, well, here are all the percentages. All right, what happens if we just add those up? All right, it turns out that that's 100%. All right, so is the answer 0%? Like neither? No, that is in fact not the answer, because of this overlap. Right? What we're actually doing here is, it doesn't seem like it, but we're counting this 10 twice. What we need to do, and this is why drawing the Venn diagram I think is so useful, is we need to figure out how many only like Sprite. Only Sprite. Well, in terms of the Venn diagram, that's this area, which this chunk is 10%, that's 55%. Well, this is going to be 45. It's going to be 0.55 minus this intersection piece. We can do the same thing over here. How many people only like Fanta? Only Fanta. Same deal, right? So we could take away that 10% piece, and we have that. Well, we have only Sprite is 45%. We have only Fanta, which turns out to be 25%. We have both, which is 10%. And if we were to add those up, we end up with 80%. Right? We have 4, 5, 6, 7, 8. So quite different than this 100%. So how many are outside of all of this? Out here, whoops, that's not a G. No, neither is this space outside of the circles. So this is going to be 20%. So oftentimes you're not given all of the breakdown and some of the categories, like neither was never specified in here. So drawing the Venn diagram, you can really detail it out and say, you know, what all the different pieces are. And so to answer this question, there's actually 20% who like neither. All right, and here's another question, which I think gets even a little bit more interesting. What's the probability of a randomly selected student liking Sprite or Fanta, but not both? So this is, Sprite or Fanta. It's an OR. What's our rule for OR? All right. We have the addition rule when we have the OR. But remember when I first introduced the addition rule for OR, I told you it got more complicated. And it got more complicated for joint variables, and here we are. So what we're going to do is use the straight addition rule, and I'll show you why it's wrong. And then I'll show you how to do it right. So here, if we are going to use just the straight addition rule, we have the probability of Sprite or Fanta. And I'm saying is not going to be equal to the straight addition rule of probability of Sprite plus probability of Fanta. Because 55 and 35 is 90%. Well, how could 90% like either Sprite or Fanta when we know 20% like neither, which means really this is an 80%, the union of these two is 80%. This is higher than the total that like both. So this can't be right, and in fact it's not. And the reason why it's not is actually very similar to why when we ended this up and got our 100%, and why that was wrong. Again, it all comes back to this intersection being counted more than once, and that throws off our totals. So that 100 isn't right, this 90 isn't right. For the same reason, what we have to do is get rid of one of these 10%. All right, so let's drill into this a little bit deeper. All right, what we're looking for is Sprite or Fanta. All right, we now know that adding the 35 and the 55 gives us too much. There's an issue with this centerpiece. If we were to diagram just the Sprite or Fanta, really we're talking about the union of those two circles, which is this area, like that. Now, this area really you can see is made up of three kind of sub areas, which looks kind of like this. And I've colored them nicely for you. Now, you can see that if we add this circle, that's the blue and the orange, and this whole big circle of the Sprite is the green and the orange. So we have orange in two different places. So what we need to do is have it in only one place. So we're going to have, maybe the 55. There we go. This is 0.55, which is going to include this 10, so we don't even need that 10. And this is going to be 0.25. Now, there's lots of different ways we could do this. Do we have to include the centerpiece on that side? No, we could put it over here and use 0.35, which is the whole circle, and 0.45, which is just the green area. Or we could do it another way, which is perhaps the more typical way, which is to say, all right, 55 and 35 are too much. It counts this middle piece twice, so let's just subtract that middle piece once. And if we do that, it all straightens out nicely, which now makes much more sense because Sprite or Fanta, again, is this union, which is everything that's not outside. So if it's 20% outside, it's got to be 80% inside. So that makes much more sense. Now, and these are now equal. We have to sort of change this a little bit. If I want to make this equal, I'm going to have to subtract something. And that thing I'm going to have to subtract is this intersection. Well, how do we describe that intersection using probability notation? Well, that's the Sprite and Fanta, because it's both. So this is the modification that has to be done to the addition rule for an OR when it's a joint event. because there's overlap. We have to get rid of one piece of the overlap. We can use set notation to write this out as well. Set notation, hopefully you did when you did Venn diagrams, whenever you did that. This sprite or Fanta, as we said, is the union of the two. So the symbol for that is the union. All right, is the sprite plus the Fanta minus the intersection, and the symbol for intersection is that. I'm hoping that that's recollection. There's some recollection of that from your past. When you see formulas sometimes given to you in books, they'll use this set notation to tell you. But we can actually have a nice little translation key, right? Intersection is really the and. Union is really kind of the or. So whenever you come across a joint variable like this, little bells and whistles should go off that maybe if it's an or kind of thing, then you're going to have to deal with this joint variable issue. I want to also draw your attention to a fact which sometimes gets overlooked. In all of these questions, this is actually a single event kind of probability question. Notice we're just selecting one student. We haven't even gotten to the questions about, well, what's the probability of selecting, the first student liking Sprite and the second student liking only Fanta? That's more of a compound event, multiple event probability. We haven't even started that yet. That gets actually more familiar. That's actually going to be very much like the tree diagram. And we're going to need to use this concept in order to get some of the probabilities to fill the tree in. So here's a compound event kind of question. If two students are randomly selected, what's the probability that the first will only like Fanta and the second will like neither? All right, so it's a compound event. We have two students being randomly selected. It's a joint variable because there is a possibility that some students might like both Fanta and Sprite. So we have to be a little bit careful about all of our probabilities. Let's get our Venn diagram back. There it is, and I've shrunk it down to make it a little bit more convenient. So now this is, a probability tree, a tree diagram that we need. Only it's going to be a little bit different because what are all the possible outcomes? The last tree diagram, it was either you get a diamond or no diamond. Well, you randomly select a student. How many outcomes are there? There's only Sprite, only Fanta, both, neither. Right? So what we need to do is write them all out. And so it's not going to branch in quite as familiar a way, but it's still a tree diagram. Here's the beginning of it. We have our start. Right? This is our student number one that gets selected. What's the possibilities? They like Sprite. They like Fanta. They like both. They like neither. So it's all these individual areas within the Venn diagram. All right, now, each one of these will branch off and have four possibilities: Sprite, Fanta, both, neither. So this actually gets, kind of big, kind of quick. Now, because it gets kind of big quick, I'm not going to fill the entire thing in. We have a specific question we're trying to answer, right, which is, what's the probability of Fanta and neither? That's our question. So that pathway, right, is Fanta neither, right? That's what I'm looking for. So that's what I'm going to fill in. Now remember the original question. How many students are there? There are 40. So you have to ask yourself the question, is this a dependent or independent variable kind of question? Does the probability of the second event depend on the probability of the first event? Well, because there's a finite number of students, it's like a deck of cards. It's like that example we did before. So this is in fact a dependent scenario. So we can say, well, in this first set of students, how many like Fanta out of the total? Right? Well, we already know that 25% of all 40 is likes Fanta. So we can fill in our 25% there. But what we also have to do is, because in this path, the first student likes Fanta, so we're taking one student out of that category. So we have to figure out how many students there are that like Fanta to begin with. Well, here we are. If 25% like Fanta, and there are 40 total, 10 students like Fanta. And it's in a different color. Let's do this. I'm going to kind of write there are 10 students. 10 students that initially like Fanta. Well, one of them is taken out. That might or may not have an impact on the second one. We have to figure that out. So here, this is all kind of initial, right? Before student one. Before student number one is removed. Right? 10 students like Fanta, 8 students like neither, because that's 20%. All right, so out of the 40, we remove the one who likes Fanta. Is that going to change the number who likes neither? No, it's still going to be 8. But what does it change? It changes the total number of students. So now here, we're going to have 8 students not out of 40, but 8 students out of 39, which are going to like neither, which gives us a probability of 0.205 of drawing a student that likes neither on the second student. Now we have the information to answer this question. Probability of Fanta and neither for the first event and the second event. Well, that's multiplication rule. Of Fanta and neither would be probability of Fanta times the probability of neither, which ends up looking like this. Here's the answer. A little over 5% chance that the first student will like Fanta and the second student will like neither. All right. This is now just sort of like a pretty standard multiplication rule, picking off the probabilities from the tree diagram. How we got the probabilities in the tree diagram, right, was kind of tricky though. We had to, really think through, is this dependent or independent? Notice actually we didn't really deal with the intersection, having to subtract that away. Why didn't we have to deal with that? Well, because this was an and. If we were going to deal with an or, then we'd have to deal with that. But maybe I'll cut this video here. I haven't done the first disjoint example. It would be nice to do a compare and contrast. Maybe I'll do that in a different video.